We are almost at the end of Unit 1 that deals with vectors. However, there is a small topic which I thought I should end this unit with, and that is about a general doubt which many students always had in my class. I used to ask them the question, what is the requirement for some physical quantity to be called a vector? So, invariably they used to say it should have a magnitude, it should have a direction. But then I used to ask them, is angular displacement theta a scalar or a vector, because it has got a magnitude, it has got a direction, clockwise, counterclockwise, you can add them like that, theta 1 plus theta 2. So, and do not even think about 2D, the angular displacement can also be in 3D, right. So, under that situation, so what do you call angular displacement, a scalar or a vector? So, our question today is whether, okay, let me write it, is angular displacement a vector? Now, the answer to this question is both yes and no. And how is it so? Let us say A, the answer is yes if the angular displacement theta is very small. In fact, there is it should be infinitesimal. Okay. If the angle is infinitesimal, the angular displacement through which it has moved, then it is a vector. Then answer is no if it is a finite displacement. That means, if theta is a large value which is not infinitesimally small, then you cannot call it a vector. Now, why so? There is a very nice way of mathematically proving it, but we will not go into that. I will just demonstrate an experiment sort of thing through which you can realize why this is so, and we will come to the proper derivation or proof, mathematical rigorous proof of this fact once we come back and learn about all the angles, something called Euler angle. So, once we read about them, once we know how to combine different angular displacements properly, mathematically I mean, then we will come back and prove these things rigorously. But for now, I will just show you one experiment. Okay. Now, for that, I will suppose take this book, and we will try to see that angular displacement, when it is of finite size, it does not obey the law of addition of vectors. Okay. So, to show that, what I will do is, let us see if I can go to the next page to have a clear picture, and let us say we have, say this is your x direction and this is your y direction, and the z direction is coming out of the blackboard. Okay. Now I will keep the book, the starting position like this, okay, and then I will sorry about that. Then I will give it some finite, or to be precise 90 degrees of angular displacement in two ways. First I will rotate it about x axis and then about y axis. So that will be our case 1. Say case 1 is 90 degree clockwise about x, and case 2 is x and then plus 90 degree clockwise about y. So that's what we will do, and I'll just erase this part. Okay, so this is our case 1, and then case 2, case 2 is 90 degree clockwise about y first. See, now I have just switched the addition sequence. That means we are trying to see whether the addition of angle is commutative or not. Okay. Then plus, after that we will have a 90 degree clockwise rotation about x, and then we will see whether we are getting the same end result in both the cases or not. So let us see. So this axis I have drawn just to keep the things in proper perspective. Okay. So I am starting like this, and now I will have a 90. So case 1, clockwise rotation of 90 degree about x. So that is x axis. So now clockwise about, so this way we will rotate. Okay. So 90 degree clockwise. So that is how we got. Okay. So then what? Then about y I will have in 90 degree clockwise. Okay. So just a minute. Now when I am saying clockwise, I am seeing, you know, from the axis which I am considering. So when I actually turn by 90 degree about x, looking from x side, it was clockwise. So that's what I meant. And similarly now looking from y, we will have a clockwise rotation of 90 degree. Okay. So this is how it will become. Fine. That means this is the configuration which we have come up to. So in this case, I'll just show you a little bit that, okay, if on the top the cover is shown, and on the back you can see the written portions. So that's the configuration we have reached up to in case 1. Okay. Then what? So okay, so case 1 result I can just show here, that we have got something like this, and the top is here. Okay. Yeah. And case 2, so I'll start with the same initial configuration, and then I'll first have a clockwise rotation about y looking from y side. So looking from y, I will have a clockwise 90 degree rotation, right? So I have finished the first one, and then I will do a 90 degree clockwise about x looking from x side. So this is what I will do. So see, the configuration I have come to is this one now. So that too on the width side, not even on the length side. So this was the length side of the book, and this is the width side of the book. Okay, so this being the thickness. So in one case, in case 1 we started, in both cases we started like this, but in case A, case 1 we ended like this, and in case 2 we I think ended like this. Okay. So that tells us that the addition of these angles is not even commutative. So obviously, if the rule of addition is not followed, even the simplest rules are commutative, it is one of the most important rules, then how can it be called even a vector? Now coming to say small angle condition, that is going to be very difficult to show it here with this experiment. Using some software, if you can rotate properly by small angles, maybe it's possible, but I'll try, but I don't think it's possible. Let's see. I'll just try once, but I'm not sure whether it will work or not. Say about x, I'll say rotate by 1 degree clockwise, say like this, ठीक है, and then about y I rotate 1 degree clockwise, so like this. Okay, so something like that I got, and let's see. So this is the kind of configuration a small for a small angle I got. Okay, I'll start like this. So I started like this, a small angle about x in clockwise and a small angle in about y axis. Okay. Now let's see if I do the opposite or the reverse order. I'll take this, the y is so small angle about y, looking from that clockwise, so like this small angle, and then from x a small angle about x, looking from x side a small angle in clockwise, so like this. See that it's almost, they are looking very similar, because we are, even in this case we are having a angle of around 10 degrees or 15 degrees or so, and that too I am not able to move my hand so precisely, but still we are able to see that the final position is almost like this, which is more or less looks at least similar. So, and then mathematically actually you can prove that when you go to infinitesimal small quantity, when that is the theta tends to 0, the final configuration in both cases will be exactly equal, and that is how you say that if theta is infinitesimally small, it is a vector, and if it is a finite value, it is not a vector, and that is precisely why your angular velocity is a vector, because that you do for how do you get angular velocity? D theta over, or change in theta over change in time, when change in time becomes tends to 0. That means in that particular case change in angle also tends to 0, which means in that condition you can consider that to be a vector. So that is why angular velocity is a vector, but angular displacement, it is a conditional vector. So that is what I thought, it is a very interesting fun fact in a way. So I thought that is the best thing to end the unit, and from next unit we will see systems with lot of forces, lot of moment and lot of couple moments. See you then in the next unit.